Ciphers is we now have to decide how to use them. So this is what is called a mode of operation. So a block cipher really is a primitive. We rarely use it on its own to encrypt data. If we do, just take the inputs, split it into pieces, and encrypt it. We have what is called electronic codebook mode. Does anybody remember why this is a bad mode you should never use? Yes. Right, it's deterministic, so if you ever encrypt the same thing twice, you can see that the same thing comes up. So you remember there was a picture of a penguin. When we encrypted it, you can still see it was a picture of a penguin because every block that was white encrypted to the same output, and so you could still see patterns from the input and the output. So ECB mode is a bad mode. Another mode we could do was like a one-time pad, and this is called counter mode, where when we do encryption, we're going to pick this random initial vector we call ciphertext 0 or C0. We then increment that, encrypt it, take the output of this encryption, which we call P1, and we XOR the message with P1. So in this case, we are not directly encrypting passing the message through the ciphertext. We are just passing this initial vector counter through the ciphertext, and then doing XOR after it. So this is like the one-time pad, remember, where we XORed the data with the key, but here we're XORing with something else. So when we decrypt, we basically do the exact same process in reverse. So it has properties like the one-time pad, that if you use the same initialization vector twice, really bad things happen. And also, if you can sort of, as you saw in the homework assignment, you can substitute ciphertext for other pieces of ciphertext. And so this does not make sure, this keeps your data secret, but it does not do anything to stop people from changing your data, because you can flip individual bits in the data if you want. So what is better is CBC mode, which is a real mode people actually use, cipher block chain. Here the idea is that once we encrypt something, we're going to use that encrypted value to XOR into the next block of data before we encrypt it. So we're basically sort of doing to some extent a linked list. So we start off with some initialization vector. When we encrypt a block, we're going to XOR the data with this previous ciphertext, and then we'll encrypt both. And then we will use the output of that to encrypt the next block. So one thing to note here is, if I change, say, block C1, suppose I'm an attacker who modifies C1, what parts of the decrypted message get changed? How much will be changed? Will I change the whole decrypted message, everything after M1, or will I only change parts of it? Does anybody remember? It turns out you would like it to change the whole thing, but it does not. So that was a good guess, and that would be a better system. There are other systems that do that. What happens here, if you change C1, when you decrypt it, you will clearly change the output of the decryption function, which is sort of running everything upwards instead of downwards, which means that M1 will change. So the other place that C1 is used is when we take C2 and decrypt it, we're then going to XOR the result of that with C1 to get M2. So M2 will change. But if you look at when we try to decrypt C3, when we decrypt it, we're going to use ciphertext C2, which we haven't changed. So it means that we can still decrypt M3 correctly. So here, changing any block of the input of the ciphertext will change 2 blocks of the clear text you get or plain text when you decrypt, but that's all that you get. So depending on the data, you might not get great integrity properties here, that you can change data in ways that might not be visible. Okay, so that was kind of the basics for block ciphers. Another thing we talked about was message authentication codes. Here the problem is we want to solve this integrity problem. We want to make sure that messages haven't been changed. So a good way to do that is to have some key that we actually use in generating this hash. And you probably saw in homework 3, what happens if you don't use a key in generating the hash is that anybody else can potentially generate their own hash and replace your hash with their hash and still modify your data. So what we do in sort of an official HMAC is we will take the random key, we will XOR it with some pad value, some randomness, and then append the message, run this through this hash function H. We'll take the output of that, prepend it with the key XORed with another random pad value, run it through the hash function again to actually get this tag we're going to call T. And so the idea here is that if you want to modify the message, you cannot just sort of extend the message, add more data, apply, keep on running the same hash function and change the hash function, because we're taking the message after it's been hashed and then hashing that output. That kind of seals the hash in so it can't be modified. So this makes it sort of reasonably more secure. So whenever you're sending data encrypted with CBC or with counter mode, you would like to do an HMAC also so that you can make sure the data hasn't been modified. Any questions? Okay, another thing we want to do is we want to sometimes take passwords and encrypt data with it. So I mentioned before there's a protocol called Kerberos, which we use for logging in for the CS department. The way it works is you send your username to a server, the server sends back some data encrypted with your password. How do we encrypt data with your password? Well, we want to make a key. So a bad way to make a key would be to just take your password and hash it. Just do a simple one hash. And the problem is that your key isn't very random. And as you saw also in homework 3, using a dictionary attack doesn't take that long. So we'd like to make sure when we encrypt things with a password that we make it very expensive to do a dictionary attack. And we do that by doing lots and lots of hash functions. So what we can do is we can take a password, append the salt, append some number to it, so we can get different unique hashes for different purposes, and then apply hash function lots and lots of times. So we can make this arbitrarily slow, the same way that Bitcoin is made slower by needing more bits to do more hashes to sort of find, to sort of validate transactions. We can apply more hashes, so if a hash takes a microsecond, you might want 1,000 of these to make it take a millisecond or something like this. So the whole purpose of repeating it is just to slow down dictionary attacks. And then the salt means you can't sort of pre-compute a big dictionary offline and use it on every password. Okay, so that was it for HMACs, symmetric encryption. Questions? Hopefully this has all come flooding back into your brain. It's all been stored very deeply and it's sort of swelling up and heating up your brain and you're nice and cozy. So the next thing we talked about was public key encryption. The idea here is that we're going to create a pair of keys, or asymmetric encryption it's also called. So instead of having a single key we use both for encrypting and decrypting, we're going to have a pair of keys with the property that we can encrypt or decrypt with either key, and the other key will do the opposite operation. So if we encrypt with PK, we decrypt with SK. If we decrypt with PK, we can encrypt. If we encrypt with SK, we can decrypt with PK. And so the normal usage for this is that we keep one of these two keys secret, and then we publish the other key so everybody can use it. This means that if anybody who wants to can encrypt something that only we can decrypt, and we can encrypt something everybody can see that we were the ones who encrypted it. Yes?
Arrow or arrow, SSO arrow, but actually we didn't have added the checksum for the encryption. So
right. So what it says is that the algorithm allows you to have an error. It doesn't require. So we saw with symmetric encryption that you could not produce an error because every single bit pattern was valid as ciphertext. Here we're saying it may be in sort of the general version of encryption that you can detect errors on decrypting. It doesn't say it's a requirement. You might decrypt things incorrectly, but you're also allowed to have an error saying you can't decrypt it. So there's some public key mechanisms where when you encrypt something, it gets much, much larger. And in that case, you could sometimes detect that it's an invalidly encrypted message. Okay? So there are a bunch of details on how RSA works. The key thing to remember is that we have some large number n, which is the product of two large prime numbers. The key property of RSA is that it's very hard to factor this number n to find those two prime numbers. And that is where that is sort of the notion of where the security comes from. That it's very easy to calculate n if you know the prime numbers. It's very difficult to calculate the prime numbers knowing n. So what we have is the public key then for anybody that they publish is going to be that number n, which is the product of the prime numbers. The secret key, I think I have it on the next slide. So the there are these two other numbers, E and D, which sort of correspond to different numbers you exponentiate with to do encryption or decryption. So to encrypt something, we're going to take your message Y, raise it to the power E, and take the modulo over that, that number N. That is the encryption mechanism. And E is a fixed value. It is the same for everybody. So to decrypt it, you use the secret number D, which you have not published, and you encrypt it, exponentiate it modulo N, and that does the other operation. So that is sort of the basics of RSA. There's certainly a lot more details in the slides. Any questions on RSA? Okay, so one of the challenges is if we give out public keys, how do we know we got the right public key? If you give me your public key, how do I know that it's not actually his public key? Because I have no reason when I get the public key to know that it came from you. So this problem is solved by having a certificate authority. The key idea here is that when I start running, I am given a set of public keys for certificate authorities that I trust in advance out of band of anything else. So you can imagine when you buy a laptop from Dell, Dell pre-installs a bunch of certificates for certificate authorities they think you should trust. When you install Windows, Microsoft might install these things. So you know these before you do anything else, and we want to use that information to bootstrap knowledge of somebody else's key. The way we do that is by having a message that is going to be signed by a certificate authority that has a name, Alice, and it has this modulus, this number N for Alice, which is her public key. And this is going to be signed by a certificate authority, which means that the certificate authority will compute a hash over those two parts of the message and then encrypt it with the certificate authority's secret key. Only the CA knows this, but I know the corresponding public key, so I can compute the hash myself. I can decrypt that encrypted hash. I can compare the two values and say, yes, this is indeed a message from the certificate authority. I trust the certificate authority because Dell told me to. So I trust that this number N corresponds to the name Alice. So that is how we sort of learn what public keys are in an authenticated way, so we actually believe the results. So we can go further than this by having a chain of certificates. So it may not make sense to say there's these 20 certificate authorities that will sign every single certificate in the whole world. Instead, what they may do is say, we will sign a certificate for all of Facebook up here and saying that any subdomain under facebook.com has this public key signed by the certificate authority DigiCert. Facebook can then, I don't think I have a good picture for this, Facebook can then create their own certificates using that and sign them with the key, with the corresponding secret key for that public key. So they can have certificates for individual servers or different websites underneath Facebook. So this becomes a chain where we will have this So we will end up with a chain where we might have a certificate for an individual domain under Facebook, like login.facebook.com, with a public key for that website. This will be a certificate that is signed by the secret key for Facebook. And so I can then look at this certificate for Facebook, see that this is the corresponding, sort of verify the signature here with this public key. And then I can look at this certificate, and I can use the public key that I already know to verify that this signature comes from DigiCert. So this lets me have a whole chain. Instead of having a single set of servers issuing all certificates, I can say there's a chain here. The other thing that goes into here is some information about what the certificate is good for. So I can say this certificate is good for issuing more certificates. And I might say this certificate here is only good for logins. So I can say that you shouldn't believe, I don't trust this certificate here to be a certificate authority for more certificates. I only trust it to do TLS or SSL or something like that. The other thing I can do here is I can say this is good for issuing certificates, but only for domain names ending in facebook.com. I do not trust them to issue certificates for google.com or cs.wis.edu. So I can scope exactly what powers I sort of give to this. The final thing I put in here is I can also say, how do I know who Facebook is? What verification did I do as a certificate authority? So one thing is called domain validation. Domain validation says at the time you asked for a certificate, you were the owner of that website. And so you can do this, for example, by going to the domain name and reading a file and making sure that it's something that has the appropriate value, only that the domain owner could put there. So this just says you own the domain for the 2 seconds it took you to get a certificate. Another thing is extended validation, which says, we went and we talked to a human and we looked up your company offline and figured out where the company is, and we have pictures of your buildings, and we actually know you really are Facebook. So this sort of says just how much trust should you put in the fact that this is really a real company versus some fake-o company. Yes?
Other ways to tell if somebody had gotten a certificate for your domain before you owned it?
There could be. So you could, I don't know if there are actually ways of doing that, but you could go to, for example, DigiCert and the other 21 top level places and say, did you give out any certificates for this domain previously? The other thing you can do that happens is a revocation list. So a revocation list is a list of certificates that were handed out that are no longer good. Suppose Facebook loses their secret key, it's not secure anymore. They want to make sure nobody trusts this certificate anymore. So they would tell DigiCert, please revoke this certificate so it doesn't get used anymore. So a certificate authority could revoke any prior certificates that were out there for your domain. Okay, so that was it for certificate authorities, asymmetric encryption, and block encryption. Any more questions before I move on? Great. Okay, so the next thing we covered was network security, and we had a threat model of who could attack you. So one thing was malicious host. We see in the upper right this red machine out there. This is a malicious host that is trying to attack you in some way. We have subverted routers or links. So we have the red router on the left, which might do things like snoop on your packets, send your packets to the wrong places. And we have malicious ISPs or backbones. We just heard about this with the Route 53 attack, where it wasn't a malicious ISP, but a poorly acting ISP allowed themselves to sort of take over part of the routing infrastructure. And so these are all entities in the system that might not do the right thing all the time that we have to worry about. So we talked a lot about the protocol stack. Sort of at the top level, you have your own data. When you send it through some application like HTTP or mail, that protocol adds its own header, an HTTP header or an IMAP header, SMTP header. When we send it over TCP, TCP adds its own header. If we then use that over IP, IP adds a header. And at the bottom, we have some network layer. We have a physical layer like Ethernet that actually sends messages in a local area. So the key thing about this stack is that each level does a different purpose. At the bottom level, Ethernet is the physical layer, and it really cares about sort of getting packets from you onto the internet or getting packets from you to other machines that are very close by to you, sort of in the same building at the same institution. The IP level really cares about getting individual packets anywhere in the internet. So it has addresses that are supposed to be globally unique addresses, and it has routing directions that say, given any address, I can correctly deliver that packet to somebody who will get it to that final address. At the TCP layer, we don't have addresses anymore. What we do have are port numbers, which will tell you what process on an end host should be receiving this data when it comes in. And it has information that goes, instead of sending packets, we're now sending a stream of bytes. So TCP gives you sort of an infinite stream of bytes you can keep appending to, and it handles reliability and reordering. So if packets get lost or dropped, TCP will fix that up. IP does not care. IP and Ethernet don't care if messages ever get delivered. That's not its problem. Their problem is to just get it closer to the destination. And then at the application level, this is where they pass information about how to use the data, how to interpret the data that's actually being sent. So, of course, with any stack of software, there are bugs in every layer of that stack. So at the bottom level, there's no authentication. We have these addresses called MAC addresses, which is a 48-bit address for Ethernet. And every network card, when you buy it, comes pre-installed with a MAC address delivered by the manufacturer. And to find a MAC address, there's a protocol to do that. That's not secure. One of the things you can do is you can change your MAC address. So if you know a MAC address of somebody else and you want to get their data, you can change your MAC address to be their MAC address instead. This is critically important when people are using MAC address for security. For example, internet companies will often say you can only connect to your internet provider from a certain MAC address to be more secure. Of course, everybody in this room would then change the MAC address in their computers so that they don't have to use that particular computer anymore. So the problem is Ethernet knows MAC addresses. How do we deliver packets to IP addresses? There's a protocol for that, ARP, which is the Address Resolution Protocol. It effectively works by broadcasting a message locally saying, hi everybody, I'm out here in the network, here's my IP address, here's my Ethernet address, I'm looking for IP address, some IP address, does anybody have it? And anybody in the network who hears the message can then respond, if they own that IP address, say, yep, that's me, send your packets to me. As you can see, that's not a very secure protocol, because if somebody's trying to send packets to you, I could respond first and say, hey, yeah, that's me. And it turns out that computers will very often, if they get multiple messages, there's a variety of ways they could respond. At one point, they would take the last message that they received. So you could just wait to see, I could just wait to see a message that was destined for you, and I could just send my own message saying, oh wait, no, that's actually me, and people would believe it. Now, operating systems typically use the first response they get, figuring that it's hard to be first, it's easy to be last. But it means that I can sort of very easily claim any IP address I want on the network. So this lets me, for example, if you're trying to connect to a printer on your network, I could pretend to be that printer, and then you would send all your data to me. I could decrypt the PDFs that you're printing, see what you're printing, as well as sending those packets to the real printer so that it actually gets printed out and you don't know anything about it. So this is a pretty insecure protocol. The other place this comes up is 802.11 or Wi-Fi networking, where we have base stations that have MAC address, that have SSIDs. So when you connect to a base station, you'll say, hey, I want to connect to UWNet, and UWNet will say, okay, that's me, connect to me, here's my MAC address, there's some authentication. Let me just see if I have any, oh, I can't go back. So the challenge is that I could put up a server for UWNet also, which you might try to connect to. I could put up a fake login screen that would ask you to log in. I would just collect your password, you'd happily give it to me, and then I would both have your password and you'd be sending all your data through my network switch, and I could see all your data and I would have your password. That would be a great attack to do on someone. And the challenge is that there's really no way to prevent somebody from putting up a Wi-Fi access point with any SSID that they want to. So this is why you actually have people who work for the university who, if you do this, will run around very quickly and track you down and take down the wireless access point. Because they don't want rogue access points floating around campus. Okay, so moving up the stack to IP. One of the problems with IP is denial of service attacks. This is where somebody sends a lot of traffic at you, and they send enough of traffic to you that you can't serve legitimate customers anymore. What you would like to do so one way to do this is something like a ping, just send a whole lot of ping messages, very cheap to send. One of the challenges is you would like to not actually be caught. You would like, as somebody, whenever you do an attack, you'd like people to not be able to track you down. If you send messages from your own IP address, it's pretty easy to figure out, where you came from, to track you down, talk to your ISP, and complain. As an example, if students on campus use BitTorrent to download pirated movies, pirated music, the university gets email from an organization saying this IP address registered at the University of Wisconsin was used to download pirated material. You know, you better warn this student or tell this person not to do it anymore. And they can do that because they know the IP address belongs to the university, and the university knows for every IP address pretty much who is behind that IP address at all times. Every time you log into UWNet, for example, the university records, you know, Jane is logged into UWNet with this IP address between noon and 2 o'clock today, and she was in the education building. So they know who you are, where you are, and what time you are from your IP address, so they can pretty clearly identify you're the one launching an attack. So how do we do this? We send fake source addresses, right? We just say, put in somebody else's IP address instead. This is easy with IP because we're just sending individual packets. So we can just pretend to be somebody else. And this means when you try to track down who it is, then you see the wrong person, you don't see anything. The other thing that's nice is you can put in thousands or hundreds of thousands or millions of different source addresses so that nobody can sort of tell at all who was sending these packets. And it also means as the defender being attacked, you can't just block one IP address to prevent the attack. You have to block, you know, you're getting millions of addresses, you can't block them all. So it's harder to defend against. So the problem here is that we allow you, or we used to allow anybody to send a packet on the internet with any source address they wanted to. There was no restriction on what addresses you could use. So what we can do about that is we can tell ISPs you really should only let packets onto your network, onto the internet, for IP addresses that you own. We just saw an example of Route 53 where this didn't happen. But in general, most ISPs at this point will prevent you from sending a fake IP address, data with a fake IP address. And at the university, they can sort of, when you connect to UWNet, they can say, we give you this IP address. If you try to use any other IP address, the university will block you from sending that packet. They will filter those packets out to prevent you from doing source IP spoofing. But there's other things you could potentially do if you can do source address spoofing. So one thing you can do is what's called a reflection attack. So you can send a packet to some other service on the network with a fake source address. When that other service sends a response, the response will go to that fake source address. So I can do a DNS lookup, for example, and I can give your IP address as the source. The DNS server will do that nice lookup for me. It'll send back a response, but it'll go to you instead of to me. So if I do this at lots of different DNS servers with the same address, all those DNS servers will do a DOS attack against you on my behalf. And they have no idea. So this is another reason that sort of verifying source addresses is so important. Questions? It's all going pretty fast. Okay, so another problem at the IP level is fragmentation. So we have this problem that IP is responsible for delivering packets anywhere on the world. It also turns out that the maximum size packet is different on different networks. So on Ethernet, it has often been 1,500 bytes. On other networks, it's 512 bytes. Sometimes on Ethernet, you can send 64 kilobytes in a single packet. This means that if you transition from a network that has large packets to a network with small packets, you have to break that IP packet up into two pieces. This is called fragmentation. It is then up to the receiver of the packets to reassemble those packets properly. So one of the problems this can do is this can allow you to send traffic where if you look at the traffic going by, you might not see that it's malicious. And this is relevant when we talk about intrusion detection systems, intrusion prevention systems, and firewalls. So for example, if we send this packet that says username and we say offset 8 is nice, and then we send another fragment that says evil at offset 8, we now have inconsistent data on the network, and we don't know what will the end receiver actually see. Will they see nice or evil as the username? And we don't know in the middle of the network because we don't know how the receiver will actually reassemble these fragments. So this is one way of evading firewalls and intrusion detection systems by fragmenting packets in an ambiguous way. But if you know, if you know, for example, what Windows does or what Linux does, then you might be able to sneak an attack by them. So moving up a layer to TCP, hopefully everybody is very familiar with this from the homework. So we have the basic TCP handshake where you send a SYN packet to the server sends a SYN-ACK packet with a its own sequence number. You then send an ACK packet. This is called the three-way handshake, and there's multiple sequence numbers. So the problem here is that people sort of assumed this was secure, that the sequence numbers were unguessable, so that you knew if you got a packet with the right sequence number, it actually came from the server, and people rely on this for security. The challenge is that, actually I'll get to it, I'll say it now, but the challenge is that if you can guess a sequence number, you can inject a packet into the middle of a TCP stream. So even though, for example, you logged into a server remotely, I can then change the data you're sending by injecting packets into your TCP sequence. And the server might have checked your password already, so after you send the password, I can start sending bogus data. So another challenge is that the system requires that the server hold data. When it sees a SYN packet, it has to remember the client sequence number, its own sequence number, so that it can respond properly later. So it means it has to allocate memory. So you as an attacker can flood the server by sending millions of SYN packets, causing the server to allocate lots and lots of space until the server runs out of space and can't accept new connections from legitimate customers anymore. This is called a SYN flood, and I think you all know, hopefully by now, how to detect these in an intrusion detection system. So here is what I was getting at about predictable sequence numbers. Where if you know the sequence number, then you can inject commands into a stream of data. And again, the challenge here is that people assume that at one layer of software, people assumed that sequence numbers were predictable. In the networking layer, people building the TCP implementations did not sort of think about the fact that people were making the security assumption and just used convenient numbers like the time of day for sequence numbers instead. And so this is sort of a general flaw we see across multiple systems where one layer of software assumes security properties of a lower layer that aren't actually guaranteed and don't exist. Okay, so that was like 3 weeks of material right there in 30 minutes. Okay, so on with networking. Domain name service, we heard a little bit about that with Route 53 today. So the DNS service is the service that says, how do we go from a human readable name like www.google.com to an IP address or multiple IP addresses for the servers that host the www.google.com web server. And we have a root, an unnamed root for this, where we have 13 or 20 root level DNS servers that do lookups here. Underneath this are different top level domains, .org, .net, .com, .tv, .info. There's lots of these now, and then underneath these there are other subdomains, and it kind of keeps going down in a hierarchy. So the nice thing about this is that at Wisconsin we can create as many names as we want because we own everything under Wisconsin. In CS we can create as many names as we want that end in .cs.wis.edu. So you might notice a lot of research projects create their own .cs.wis.edu domain name because it looks cooler. So how does this work? So to use this system, we have a DNS resolver. As a client, you go to resolver and say, will you look up www.wikipedia.org? And there's two ways to do this. One is a recursive way where the DNS resolver will do the whole lookup for you and give you back the response. The other is an iterative way where you basically will get told at each level, here's where you should go instead, and then you have to go to the next level. So this recursor here, this resolver is recursive for the client, but all the name servers on the right are not recursive. They are not doing the lookups. They are just saying, try this other place. So when you look up www.wikipedia.org, you first go to this unnamed root and say, who has .org? And the root will say, go to 204.74.112.1 to look up .org, anything under .org. You go to .org and say, do you know what wikipedia.org is? And it says, oh, go to 207.142, blah, blah, blah. That owns Wikipedia. You then go to the wikipedia.org name server, and it says, oh, here is the IP address for www.wikipedia.org. So that is sort of the iteration. So the other thing to note is that this recursor here is caching all the results in the middle. So it remembers the first time it does this, what is the name server for .org, what is the name server for wikipedia.org. So the next time it does a lookup, it doesn't have to go to the upper two levels, it can just go to the bottom level. So this is all well and good. I think we just talked about this. The problem is that it's not secured in any way. So the way that you can attack this is by injecting a fake response. So There's a couple of places you can do this. So here we are doing it when we are looking up in the name server for the actual domain, Bank of Steve. When you're looking up the address for www.bankofsteve.com, the bad guy will send a forged DNS lookup response with the wrong IP address. So in this example, we're looking up www.bankofsteve. We go to the root servers. Eventually, they take us to the Bank of Steve servers. Bank of Steve will try to respond with the right response on message 5, but we stick in a fake response in message 2A that has a fake IP address. This means that whoever looks up www.bankofsteve through this name server will go to the wrong place. So this means that if we're not using TLS, anybody connecting in an insecure fashion will just connect to the wrong machine. If we're using TLS, we will get one of those messages that says, you know, your connection may not be private. Do you want to proceed? You all know, say no when that happens if you're going to a bank. Okay, any questions on DNS spoofing? No. Okay, so IP hijacking, we already talked about today. I'm just going to skip over this since it was covered already. So the last pieces of networking we talked were sort of intrusion detection and surveillance. So intrusion detection and prevention systems, you have intrusion detection, which will monitor traffic and then will alert an operator on a problem. This means that it doesn't have to be quite as fast because you don't have the time that it takes to detect an attack doesn't slow anything else down. It just says, it sort of affects how long it takes you to respond. It also means when you're alerting somebody of an attack, you don't have to be quite as precise because it might be okay to say, I think there's an attack underway, when in fact it's not an attack and some human steps in. Second, we have an intrusion prevention system which will actually block traffic that it thinks is part of an attack. Here it has to be very fast because it is deciding for every packet, should I let it go through or not? And it has to be very accurate because if it says no incorrectly a lot of the time, a lot of false positives, then a lot of valid traffic will get blocked and your customers will be very unhappy. And a firewall is really a simplified intrusion prevention system. Typically it has sort of fairly simple rules that say don't allow traffic to certain ports or from certain IP addresses, or only allow traffic to certain IP addresses or ports. There's two general classes of intrusion detection prevention systems. One is signature-based, where you tell it this is what bad traffic looks like, or this is what good traffic looks like, filter out all the bad, or filter everything but the good. The other one is anomaly-based that sort of learns on its own, where it says, I've been seeing all this traffic, I now see something new, I don't like anything new, chances are anything new is troublesome and we're going to block it or raise a warning. So that is nice because it doesn't need administrators to keep signatures up to date. You can find attacks the moment they happen. The downside is that if somebody introduces a new application, like imagine when BitTorrent came out, it probably looked very bad and different. So it blocks new applications when they come out, which users might complain about. In terms of placement, there's two major places you can put a firewall. One is on the host, which means you can tailor it to exactly what that host is doing. It also means if you have a portable device, it travels with you. The downside is that it takes resources on the host. It's hard to administer centrally. Users tend to be sort of more responsible for them. Another one is on the network. So we have something between the outside untrusted internet and all the hosts that are on the inside, and it sees all traffic going to all hosts. So it has a better view of things. It's easier to manage. It might be cheaper to have just one box, but it might also be more accurate because it may not know exactly what's running on host ABC, so it may let through some traffic that it really shouldn't have. So one type of firewall is what's called a stateless firewall. These don't remember anything about the packets they've seen in the past. What this means is that they can be very fast and very efficient. They don't really need much memory because they're not recording anything, but they can only look at sort of the fields in the packet, the IP field, the port numbers in TCP, flags, but they can't sort of go beyond that because they can't reassemble fragments because reassembly takes space. They can't sort of interpret streams of data in TCP, so they're sort of very simple and coarse-grained, but very fast. So here's some example where you might say is that only allow UDP on port 53, which is DNS, to go to my trusted DNS server. Don't allow DNS traffic to any other machines other than my DNS server. A stateful firewall will actually remember information about what it's seen. So if it sees a fragmented IP packet, it can reassemble that IP packet. If it sees an IP SYN packet, it can look for the ACK packet and make sure the sequence numbers line up. Or if it sees an ACK packet, it can sort of make sure there was a SYN packet beforehand, so we don't, from the same address, so it can sort of look for certain spoofing attacks. Finally, we have application level firewalls. These are firewalls that sort of sit at the application level, receive the whole application message, interpret it as an application would, and then send it along if it's safe. So for example, a web proxy is like this, where you make all your HTTP requests to a machine. That machine will then send them out onto the internet. When they come, response comes back, it will look at the response, make sure it's safe before sending it back to the client. So it has sort of the most information about what's going on, but it also is unique to one application. So it doesn't work for every application, and it slows things down because it has to see the entire application message potentially before sending it along. And then another thing is sort of a common way of deploying firewalls is that we will have sort of a notion of inside, which are the things inside a company that should never really be accessed from the outside, or maybe not have direct access to the outside world. We have the outside internet, and in the middle we have a demilitarized zone where we have firewalls on either side. So the outside firewall only lets traffic, sort of legitimate traffic for those servers in the middle come through. The interior firewall will allow traffic from the inside to perhaps go to the demilitarized zone, or limited traffic from the DMZ inside, but can sort of really restrict what's happening. And so this sort of gives you two levels of defense to try to stop bad people from getting through. Okay, so we talked about policy-based IDSs, we talked about anomaly detection, we talked, so a little bit on attacks here. So one of the problems with a state holding firewall or IPS or IDS is that you have to store state. Once you have to store state about everything, you can launch an attack. So a SYN flood is an example of this, where you sort of increase the amount of state the firewall has to store to the point where it can't keep track of all of it. And then either it will reject all packets, which means that it creates a denial of service attack on legitimate users, or it will just stop filtering packets altogether, and it basically disables the system. So an IDS in particular that is not blocking packets, you can potentially overwhelm by sort of creating so much state that it can't accept new packets, it can't detect intrusions anymore. Another attack is the overlapping fragment attack. We talked about this before, where you send fragments with sort of confusing overlap between different packets. Before we said this is confusing. Here, the challenge is that the firewall, if it doesn't know how to reassemble packets, then the wrong thing will happen. Or if it reassembles packets the wrong way, it won't see the actual attack going on. And so this bypasses the policy. Another challenge with a firewall, or the way to affect a firewall, is using time to live. So packets have a time to live field that says this is how many hops through routers they can take, and if you exceed this time to live, you should throw the packet away. This makes sure that if you have some cycle in your network where you're routing packets, so I send packets to you, you send them back to me, eventually the packet will be discarded because the TTL will go to 0. This sort of prevents routing errors from killing your network. So you can use this to defeat firewalls by saying we're going to pick a TTL so that the packet goes to the firewall but does not actually go all the way to the server. So if you combine this with fragmentation, for example, we can make sure that the fragment, one of the fragments makes it to the firewall. If it can reassemble the fragments, it sees valid traffic. We then send the rest of the data that goes all the way through to the end host with different fragments that longer TTL, and so it sees a different set of data than the firewall does. So the key attack here and with fragmentation in general is twofold. One is you exhaust resources because it has to store data to reassemble. The second thing is you make sure the firewall sees a different view of data than the end host does, so that the firewall doesn't think there's an attack when there actually is an attack going on. Any questions? Am I going too slow? Too fast? Is this useful? Yes. Okay. So the next kind of attack is an algorithmic complexity attack. And the idea here is that any state holding device has to have a data structure to hold that state. And there are, mostly they will try to find some very efficient data structure with order 1 lookups, for example, a nice hash table. The problem is that as an attacker, if you know how this hash table is computed, what the hash function is, you know the shape of this, you can potentially shape your data to intentionally cause a collision in the hash table and make it have its worst case behavior instead of the average case behavior. So in this case, if we know how things are hashed, we can make the packets we're sending all hashed to one bucket. This can mean that the intrusion detection system is doing a linear operation every packet, so it goes too slow. So again, either it's a denial of service attack, or it starts dropping packets and it can't detect our attack. You can, by the way, do the same denial of service attack on applications. Apache web servers had a problem where anytime there was a slash in the URL, it did sort of a order n operation of the whole URL. If you send a sequence of 16 slashes, it would do 16 squared operations, which is 655, no, what is that? 256 operations. If you send send 65,000 operations, you could make it do 65,000 slashes, you could make it do millions of operations and slow down. So the key thing to note is, as a designer, you really need sort of to think about in a security case, the worst case performance, not just the average case performance. And then the final thing to think about is, in terms of anomaly detection, we have to think about how good does our anomaly detection have to be. So we have this example where you have a terrorist in a city of 1,000 people, so 1 in 1,000 is a terrorist. And we know that 99% of the time someone is a terrorist will have an alarm, but it also means that for every 100 people, the alarm only goes off once. So if we have 1,000 people, this means that we will have sort of 10 false alarms for every true alarm. So 90% of the alarms are going to be blaming legitimate non-terrorists as terrorists. So this is a challenge, because if you have human operators getting alerts, they're going to get, 90% of the alerts they see saying there's an attack will say that, well, there not actually be an attack. And so you really, as a designer, want to get that false alarm rate low and balance that against how many attacks you're willing to miss. Because when you reduce the false alarm rate, you're also going to reduce the chances of detecting a true attack. Okay, we're making good progress. Okay, so when we think about, so here we're talking about censorship and surveillance. So if you're trying to build a censorship system to prevent, suppose the university wanted to prevent students from doing certain illicit operations from UW housing. So they might look at all the packets that go by and decide to filter some of those packets out and prevent them. So one thing they can do is they can just look at IP headers and say, we are not going to allow traffic to certain IP addresses. If we do shallow packet inspection, we can look at TCP headers. They can say, for example, we're not going to allow any traffic to certain ports. So it used to be that BitTorrent had a well-known port number. The way you would block BitTorrent, you can't do it by IP address because BitTorrent is peer-to-peer. Anybody on the internet might be running BitTorrent. But you can say, well, it always uses port 79 or something. So whenever we see traffic to port 79, we're going to block it because we want to block BitTorrent. We can look at application headers or user data. This is called deep packet inspection. Here you can do things like filter out specific URLs, look at what domain names people are actually going to, and try to do sort of deeper levels of inspection and censorship. So how do you prevent this? So one way to do this is to do end-to-end encryption. So if the service you're talking to supports encryption, then you can encrypt the data on your side and it goes all the way through. To the other side, nobody on the inside can see what's going on. So this will prevent deep packet inspection. And because when you do TLS, it has sort of a well-known port number. You can potentially handle filtering based on port numbers as well. But we still have to send it to the real destination, so filtering by IP address will still stop this. So if I wanted to stop you from going to Google, I could still prevent all traffic to Google's IP addresses. Even though it's encrypted, it still wouldn't be able to get through. So it's not complete. So one way to solve that is called the onion router, and the onion router will obscure where you're actually sending, where data is coming from when it gets received, and where you're sending traffic to. And it does that by encrypting the data in sort of an onion of encryption layers, and then sending it through a network of lots of servers, so that no individual server knows the real destination or the real source or the final destination. So if we want to send a packet, we might first send it to this Tor node that sends it to another node, and then finally it goes to the destination. So at the destination, we don't know where it came from. At the source, we don't know where it's going. This means that any kind of filtering at the source will not actually tell you where the destination is. Filtering at the destination can't tell you where the packets came from. So you can, however, block all traffic to Tor if you wanted to prevent people from using this. So there are simpler anonymization services. One is just a single hop proxy, where you send traffic to a proxy, perhaps unencrypted, and then it will send traffic onto the server. So from the server's perspective, it looks like all the traffic is coming from one place. So this means that if the server is reporting IP addresses, it doesn't know what your IP address is. If law enforcement wants to know what IP address was used to send an email, they can't tell because the IP address used at the mail server is not yours, it's the anonymizer's instead. So the FBI does not like things like this because it makes their job harder. So how do you filter this? So IP filtering alone is pretty simple to defeat just through a proxy that will sort of forward IP packets. For DNS filtering or redirection, so this is where somebody looks up a DNS name and you filter response and sort of say certain DNS names can't be looked up or we'll send them to the wrong location. Here, having a proxy that will do your DNS lookup for you someplace else will work. For URL filtering or packet filtering, this is where encryption can help. For protocol filtering, if we're not going to allow traffic on certain protocols, here is where you can obfuscate things and sort of make one protocol look like another protocol. So we can sort of say we're going to take HTTP. People have actually done this where they say we're going to take HTTP and embed it to make it look like a DNS request. And so by sending enough DNS requests, we can sort of get an HTTP request through a firewall that doesn't allow HTTP. Okay, done with networking. 11 minutes left to talk about virtualization, hardware, security economics, and Bitcoin. So I'm going to assume that people would rather review older material than material we just covered on Tuesday, which I hope seems reasonable. So with virtualization, there's sort of there's a couple of different sort of taxonomies of virtualization. One is full virtualization. What this says is we can run unmodified operating systems that have real regular device drivers that are written to talk about the real hardware devices. We're going to emulate everything about hardware in the hypervisor, so that that unmodified operating system can run. This means when you're doing I/O and want to send a packet, the driver will do things like write to device registers. The hypervisor has to recognize those writes to device registers, interpret them as, oh, I want to send a packet, and then actually send the packet. In para-virtualization, we make this simpler by inserting new virtual device drivers into the operating system in the virtual machine. And these virtual device drivers will then directly call the hypervisor with some call that says send a packet. So we don't have to emulate devices anymore in this model. It makes it simpler. It also means that the attack surface is reduced because we have to have these very complex device models for lots of different devices with full virtualization. With para-virtualization, we can have very simple calls to do simple operations. For example, sending and receiving packets, reading and writing disk blocks. So the other thing is type 1 and type 2 virtualization. This is a stupid name that came out in the 70s. You should never name things type 1 and type 2. You should always use descriptive names. Because nobody that I know out there actually remembers what type 1 and type 2 are. But the important thing is there's two kinds. Type 1 is what we see on the right, where there's a hypervisor that writes directly to hardware, accesses hardware directly. What this means is that the hypervisor has to have all the code that manages hardware. It has to have memory allocation, has to have scheduling, has to have device drivers in it. So this makes writing a hypervisor a lot of work. Type 2 virtualization has a host operating system that provides all those functionalities, which are very similar to what an OS does. So the hypervisor doesn't do scheduling between virtual machines. Instead, it pretends each virtual machine is a process. and the host OS does scheduling. If a virtual machine needs more memory, the hypervisor goes to the host OS and says, give me memory. If the guest OS wants to send a packet, the hypervisor goes to the host OS and says, here's a packet you should send. So we're using the host OS for all that hardware management purposes. What this means is that the basis of what has to be secure is a lot larger. On the right, the hypervisor has to be secure to make sure we're securely sharing hardware. On the left, in a type 2, we have to have the hypervisor, which is smaller, but then we have the whole host OS that has a lot of other things in it that has to be secure also. Yeah. So typically, para-virtualization will have a smaller attack surface because we have these well-defined interfaces as compared to full virtualization. And a type 1 hypervisor has a smaller attack surface because the hypervisor has to do less as compared to a host operating system. And so a type 2 hypervisor will have a bigger attack surface because you have all the functionality of that host operating system, you can potentially attack it. No, the two things are orthogonal to each other. You can have type 1 full, type 2 para, type 1 para-virtualized, type 2 fully virtualized, type 2 para-virtualized. Those two axes that describe virtual machines. So one thing we might want to do is we might want to use virtual machines to measure and investigate what malware does, because we can sort of go in through the hypervisor and sort of see things that normally would be hard to see. We can sort of see the direct contents of memory. We could single step it and see every instruction that executes. What this means is that an adversary, somebody writing malware, might want to say, am I running on a VMM, which is case A, at which point I want to disable all my features. Am I running on real hardware, case B, I want to enable my features and launch lots of attacks. So this makes, the idea is to make it harder to analyze malware. And so it turns out that it's very difficult to prevent detection of virtualization, because in para-virtualization we have different device drivers. We also see that there's certain instructions that might have different results in para-virtualized versus fully virtualized in some cases. The other thing is that some operations are faster on one system than the other. So some instructions, for example, will always cause you to switch from the OS into the VMM or the hypervisor when you're running virtualized, and it will not happen natively. So just through timing, we can sort of tell the difference. So in general, it is very difficult to prevent malware from detecting it's running on virtual machines. So the other thing that virtual machines are nice for from a security perspective is that we have very well isolated systems. Normally through an operating system, we have a shared file system. So all the files that are in the file system could be accessed by multiple processes. We have lots of data structures in the OS kernel, the open sockets, open files, list of processes that are shared that could be used as an attack vector. In a virtual machine, we have a much sort of simpler set of data structures in the hypervisor. We have no shared file systems. We just have shared block devices and networks that are easier to secure because they have a simple interface, read a block, write a block, send a packet, receive a packet. So hypervisors can provide, or virtual machines can provide, very strong isolation. It doesn't mean they're perfect. So one way is that we saw, or we will see, we have seen and we'll see again, that you can sort of look at performance differences as a covert channel, where you can overuse a resource, which means that some other virtual machine gets less use of that resource and can use that to send and receive a message. So I could write a lot of data to the cache. When you run, you detect your data is being evicted. That lets you know that I have written something to the cache. Another problem is that the hypervisor is not perfect. If it has bugs, you might be able to use that to escape the isolation and compromise the whole machine. Most hypervisors have had some bug in them that lets guest operating systems sort of totally subvert the whole system. And then finally, another version of this covert channel is a side channel where one virtual machine can spy on the activity of another virtual machine by watching shared resource usage, again, processor cache, memory bandwidth, things like that. So what this means is that the amount of isolation sort of matters. So this shows for different resources, hardware resources in the system, if you're running two virtual machines on the same core and time and content switching back and forth, using these resources, how much performance degradation in the worst case can one virtual machine cause on the other? So for CPU, there's very little degradation. The reason is that the scheduler will do a good job time sharing. It will preempt one virtual machine after a certain number of milliseconds, run the other one. The network and the disk are pretty bad because they don't do a good job sort of preventing one virtual machine from monopolizing use of them. The memory system right into DRAM is pretty good. The memory controllers, because you're alternating who runs, there's no simultaneous use. And the processor cache is very bad because one virtual machine can sort of totally wipe out anything the other virtual machine put in the cache. So the cache behavior gets very bad. Was there a question over here? What is the what? Okay, so I mentioned the Zen scheduler vulnerability. So, not going to be an exam, but it's interesting. So, the scheduler normally wants to run virtual machines for some time slice. So it lets virtual machine run, and then when it uses it as time slice, switches to virtual machine 2. It turns out that in Zen, if you yielded your virtual machine right before the end of this time slice, it wouldn't account for the time that you used. It would record you as having used 0 time. And so what it would mean is that you would get to run again because you hadn't used any time up very recently. So it might actually keep scheduling virtual machine 1 over and over again. Because it is not properly accounting for the time used. So the challenge was that the timing for measuring how long you run was very coarse-grained. So as long as you yielded before that timing measurement incremented, it wouldn't measure the time. The solution to this was to actually measure the number of cycles. So it could precisely count the cycles you executed for and use that as a way to accurately measure how long you run. And there's a variety of other attacks you can do like this too. Yes?
Why does this go into the law? Because we can make a policy that each virtualization VM has a specific gigabyte disk.
Right. So the reason is that if you learned about sequential versus random access, right? So sequential access on a disk is very fast because you can sort of there's a mechanical thing called a head. You position it at someplace on a disk. And then you can just read the data as the disk spins. So you can read 200 megabytes per second. If you do random access, you have to move this disk head before every access, and it takes about 5 milliseconds to move it. So what I can do is, as my virtual machine, I can do lots of random access. That means when you're reading from the disk head is never in the right place. It's always in the wrong place. And so I can completely hurt your performance by doing that. And you can solve these to some extent. The network and disk are problems that a smarter virtual machine monitor could solve, but they were not solved in Zen at the time we took this data. Okay, so one of the major attacks we looked at in virtual machine monitors was the side channel attack, and we were attacking through code. The idea was we want to detect which code path is taken. Is EI equal to 0 or 1? And we can tell the difference because if EI equals 1, we're executing 2 more function calls than if EI equals 0. So we want to look at the instruction cache and see whether the instructions for those last 2 lines make the cache or not. So we do this by priming the cache, filling it with known data. We then run the victim here, let it run, let it access some data in the cache, and then we'll probe the cache and measure the time that it takes to access everything. And through this way, we can tell what was referenced in the cache, and we can use it to figure out, potentially, whether those last 2 lines of code were run. By knowing that bit, we actually learn 1 bit of somebody's RSA key, and we can collect enough of those bits, we can then guess what their RSA key is. Okay, so it's 10:45, so I will stop now and let you go. I can certainly continue going through this at the next review session on Tuesday. I have office hours today from 1 to 3. These are extended in case people have questions. I also want to really encourage everybody to fill out the course evaluations. We went up to 40. One more person did it since I sent email. We were at 47%. So we are very close to getting extra credit on the test. I did check with somebody whether that is legal for professors to offer extra credit for course evaluations. And I was told that I can't just give you 3 points on the exam if everybody fills it out, but I can have extra credit questions that you can use to prove how much you know. There's very sensitive rules on this. I also learned, by the way, that I can't give you cookies before the course evaluations. I did that